say if the English will be the difficult part. So
Yeah.
Shachar will tell us about pseudorandom generators for CC0P in the Fourier spectrum, low degree polynomial.
Okay, great. And this is joint work with Partha MODpMODp and Amir Shpilka. So let's just start with motivation, as I'm sure you're all familiar. So somehow the motivation for this work came from circuit lower bounds. So this is one of the most basic classes of circuits that we know quite a lot about is AC0. Okay. So AC0 is a class of, so we have circuits, there are constant depths. Circuits with the gates being AND or not, and the AND and OR gates have unlimited fan-in. So those are just circuits that look like that. So we have some gates. Some of them are, let's say, AND gates or OR gates. And we can put some, I don't know, some NOT gates in between. And we have wires all around. And we have the inputs, x1 to xn, and an output. And then obviously the basic question is what can you compute with those type of models? And as I said, we know quite a lot about AC0 circuits. So let me tell you two things. Let's do it here. So for AC0 circuits, we know functions which are really hard. So not only can you compute them, you can't even approximate them much better than trivially. So we have hard functions. So for example, parity. So this is just computing the parity of the n bits is very hard. So for example, that's I guess a result by Hastad from 86 that if you want to approximate parity, so if you're given any such circuit where the number of gates is not too large, let's say the number of gates is polynomial in n, then the probability that any such circuit will compute parity correctly, well, if you just want to guess the value of parity, output 0 all the time will be correct half of the time. So anything better than half is non-trivial, and then the best you can do is something like half plus something like 2 to the minus n to 1 over, I guess, d minus 1, where d is the depth of the circuit. And there's a result of I-type that probably can get here something like better than that, but yes, Srikant and Paul and some others are trying to understand it now. So maybe they'll tell us about it when they understand it. But anyway, but we know very hard functions for parity. And not only that, we know how to, for example, use those hard functions to construct pseudorandom generators for AC0. So what is a pseudorandom generator? A pseudorandom generator is a way to generate bits that are not random. They come from a very small sample set, but they behave like random bits. So AC0 circuits cannot separate them from uniform bits. So let me just give a formal definition.
Without saying how to prove that?
No. I'm just stating some known facts about it. And then I'm going to go into a different model, which is what we're studying today. Trying to generalize those things for more complicated model of computation. Okay. So a pseudorandom generator which is abbreviated just PRG, so I just call it PRG pseudorandom generator. We just mean some map G that maps a small number of bits, R, into n bits, and think of R as much smaller than n, such that for any AC0 circuit cannot distinguish the output of G, this G from just uniform bits. So let's say the probability that C of x is 1, where x is uniform bits, minus the probability that c of g of x is 1, where x comes from this much smaller number of bits and g stretches it to n bits. So those are very small. So this is, let's say, small. Okay. Yes, Menachem?
No, what is C?
Okay, so C is some circuit. So this is, okay, so a pseudo generator is just, so we have a family of tests. In this case, the tests are AC0 circuits. And we ask to, now I give you a small number of bits, R bits, and I ask you to stretch into n bits such that this distribution, which has very small support, only size 2 to the R, of C looks just like uniform. And for AC0 circuits, because we have very odd functions, and Noam Nissan showed in 91 that you can get those things explicitly. So I guess that's Noam Nissan 91 showed that you can use parity to build explicit PRG with the number of seeders is just polynomial in log n. Okay, so the optimal we would hope to get is log n. What?
You can actually use also any dy's independent.
So I'll get to it. Okay, good. So but the initial work said okay. Then Nissan and Vigdon generalizes it. In general, if you have any function which is very hard for a model of computation, for example, here parity is very hard. The best approximation is half plus exponentially small in n, or in polynomial in n. You can use it in some black box way to construct pseudorandom generators for this model. That's called the Nissan-Vigdon generator. I won't define it, but in particular, it gives here this very short seed length. And in fact, as Noga said, that Mark Braverman solved last year a conjecture by Nissan and Lineal. What? Maybe, I don't know. But essentially that says that any, I guess, Ry is independent distribution. Fools AC0, where R is still some polynomial in log n. So you don't have to take this special generator that comes from this Nissan-Vigdon generator. You can take any R-wise independent distribution. Doesn't matter how you make it. This will fool AC0 circuits. So that was a very, very nice result. And so as you can see, so we don't know everything about AC0, but we know quite a lot about it. So now the question is, how can we make more complicated models of computation and try to understand them as well? So one thing, for example, that we know is that parity is hard, or in more generally, modular counting is hard. So for example,
your definition of small will usually be smaller than any polynomial, or?
So you mean small here?
Yeah.
So for nothing of some epsilon, and then you can define it as a small constant, or smaller than any polynomial, or exponentially small, or whichever way you want. During this entire talk, this will just be a small constant. So d will just depend, the constant here will depend on d. Oh yeah, here, so you need to fix a d. So that's a set of depths d. So I fix a depth a priori, and then for this depth, I give you this generator. Yeah, it's a good question. Good. So actually the model that we were interested in is where we allow not just AND and OR and NOT gates, but let's say modular gates.
So what is the depth for AND
Okay.
that you can actually compute parity? There must be some.
So again, yeah, so you can do parity with depth log n.
You can always do it with log n.
Log n over log n is even better.
Yeah, okay.
Even better, okay.
Right,
That's tight. And then, yeah, that's tight. Okay.
thanks. Okay, so now the models that we'll really be studying is what happens if we allow here, instead of those gates, also modular gates. So what are modular gates? So parity is a gate that takes n bits and returns their parity, either odd or even. Let's say a modulus 3 gate will take the bits, sum them, and then return 1 if their sum is, let's say, 0 modulus 3, or and otherwise 1 if it's not 0 modulus 3, and so on. So what do we know about this model? So this model is now called not AC0, but AC0, let's say, modulo P, where we allow here this specific gate mod P. So mod P, where P for now, let's think about as a prime, is just this gate that takes n bits and returns 1 if P divides or sum. For example, you can also define other types of gates that depends on the sum modulo P. Actually, if you're working over primes, it doesn't really matter. So what do we know for this model? So actually, we know something, but much less than for AC0. Like understanding those modular gates seems to be harder. So when P is prime, we know some things. Prime or prime power. So for example, we know some facts. Well, we cannot compute, let's say, mod Q, where Q is some number co-prime to P, unless your circuit is very, very large, unless you have many, many gates, unless the size is something like exponential in n to the order of 1. Well, this constant depends on P and Q. So for exact computation, we know quite a lot, but what can we say about approximation? So actually for approximation, we can say much, much weaker things. So for approximation, so assume for now, I don't know, P is odd, then we know then the probability that such a circuit will compute parity, well, we'd also expect it to be half plus something exponentially small, because intuitively, there should, if I wanted to compute parity, but I allow you to compute modulo 3 for free, this shouldn't really help you. But we don't know how to show those things. So the best we can show is something like half plus something which is roughly 1 over square root n. Actually, there are some polylogn factors here. But essentially, we know how to show relatively weak correlation bounds, which are much, much weaker than the ones we knew how to show for AC0, which are exponentially small in n. And the problem is that we cannot use those types of correlation bounds to get any meaningful pseudorandom generators. So if you try to use those types of correlation bounds and get pseudorandom generators, then those will give you pseudorandom generators with field length which is really large. It's something like exponential in square root of log n. So I guess that's Russell's and Namnissan and Wigderson, or oh no, it's LVW. No, it's Luby, Velichkovich, and Wigderson. Sorry. Yes, right. Good. Yeah, that's I guess Luby, Velichkovich, and Wigderson from about 93, if I'm not mistaken. So we know how to get something non-trivial. What?
The V is a set theorem.
Really?
Yeah.
Ah, nice. I didn't know that. But I think those are much, much weaker than the things that we know for AC0. Here we have polylogn. We really want to get logn. Like a random construction will give logn for any, let's say, even polynomially small error. So we know that almost that. Here we know something much, much weaker. So somehow the motivation that we have in mind is to improve that, to get something better here. And we don't really know how to do it. So a way to approach is just look on more restricted models than AC0P and try to understand those models. And once we understand those models, maybe we can learn some techniques and get them to work for the more general model. So there are two interesting subclasses. So the first one is actually the one that in the title of the talk is CC0P, where we allow just modulo P gates. So we don't have n's and r's, and in fact, I'll show you in a second, this is really be a question about polynomials. Because you can always simulate those circuits by low-degree polynomials over bits. And then the other, so that's one class. And then the other class will be sparse polynomials. So why sparse polynomials? Well, sparse polynomials are just something like modulo p, and here you put AND gates. And so on. So that's just the sum modulo p of the product of variables. But the requirement here is that the number of monomials is small. It's, let's say, polynomial in n, or even smaller than that. And actually, sparse polynomials are a very tricky model. So if you're working in very large fields, we know how to say various things about them. But over small fields, we don't really know anything non-trivial about them. So actually, understanding sparse polynomials will be very interesting also in other models, also for real polynomials. So, but we don't know how to say anything non-trivial about them. What I'll say something today is about this model of CC0P. And in fact, so what I'll show is how to construct a pseudorandom generator for this model that will get you any constant error, where the seed length will just be order of log n. And it will not be via constructing hard functions. So we don't know how to construct hard functions for this model. It will be using a different route to get PRGs for this model. But not very hard.
Oh, okay. Oh, just in the approximation.
Yeah, I mean in the approximation we won't get very hard functions. But actually, even if you had so actually we have hard functions, but there are other problems. So you cannot use, so to use a Nissan-Wigderson generator, you need your model to have some properties that polynomials are too weak to have those properties. So you cannot just apply the Nissan-Wigderson generator even if you have hard functions. So hard functions will not help you. So in fact, what you need is a hard functions for a more complicated model in order to apply the Nissan-Wigderson generator, which we don't have.
What is the point of not allowing the logical gates? You can code them with this, right?
No, so not really. So to take the simplest case is modulo 2 gates, right? Modulo 2, there's nothing there, right? If you have modulo 2 of modulo 2 of modulo 2, this is just parity, right? You gain nothing there. So you can't compute AND with parities of a number.
Repeat things. I mean, you can put q times
Yeah, you
x
can.
and p minus q times y, and
Yeah.
that gives you sort of something like
Yeah, but it won't give you, no, it won't. It's a weak model. So it won't give you AND, for example. Even if you allow arbitrary size and any constant depth, it will not.
You cannot do the negation.
No, you can do negation. That's not a problem.
But you do large Fannin ends?
You have unbounded Fannin, but think about parity. It doesn't matter how large the Fannin is, it will just be parity. Right?
Here there will be functions that you cannot compute at all.
Yes, exactly. Yeah. Yeah, so somehow getting hard functions is easy for this model. The hard one case is to get pseudorandom generators. So we just state the theorem exactly. So we'll give a generator G from R bits into N bits. So let's say, so fix some depths D such that for any depths D CC0P circuit C, and let's also fix some error epsilon, then we have what we wanted. That's probability that C of x is 1 over uniform x minus the probability that C of g of x is 1 where x is the smallest string. So this is bounded by epsilon. And I have to tell you how many bits do we need. So what we need is there's some constant times log n. So at least in the regime of constant error and constant depths, we get the optimal things up to a constant, but this constant is actually very bad. So this constant is something, it's something like, so you take iterated exponentials, something like p to the d times of 1 over epsilon. So it's a tower of exponential. The length of this tower is something like p to the power d, roughly. And on the top you have 1 over epsilon. So you see, even if epsilon is slightly sub-constant, this is already a very, very huge number. But at least...
Even if it's a constant.
What?
Even if it's a constant.
Yes, but then it's just constant, right? But very large one. Yes. And so there is no reason why this should be the right answer, but this is what we get.
So again, so what's the expression? Exponentially?
It's a tower of exponentials. So this is an iterated exponential. The length of the tower is p to the power d. 2 to the 2 to the 2 to the 2 to the 2.
Okay.
On the top you have 1 over epsilon, and the length of this tower is p to the power d, roughly.
Okay. So this constant times log n.
Yes, and then this constant times log n.
In the log n is optimal even if epsilon is constant because
Just because of the number of circuits that you have, right? Just want to just by a union bound.
because otherwise it's a number of circuits that are very different from each other.
Okay. Good. So that's what we.
Yeah, what was it?
So say that you had less than log n bits. Okay, that means that there are less than n strings output. And you can make a polynomial that vanishes on all of those strings. But is doesn't vanish, is non-zero.
Yeah, but
Yeah.
it's constant. But you can take a code. So you can take many circuits that are very different from each other.
Well, that's
Yes.
I'm telling you how to construct.
I think so. Yeah, probably even for parity, right?
The family of circuits is just to take a circuit for every group of entity epsilon inputs, make a circuit that is 0 on those inputs and is non-zero.
Yeah. I mean,
So one of those can't be fooled by any.
yeah, I mean, even for parity, you need epsilon bias. If you want to fool all parities, essentially you want to be epsilon biased. So even for a constant epsilon, you need something like order of log n. Okay. So that's what I want to show. So the way towards it will be somehow to understand structures of polynomials, and for this we need to understand the Fourier spectrum. And actually what I'm going to start with is describe, so first I want to tell you that a simple observation, why is this really a question about polynomials, not about circuits? Okay, so here's a very simple claim. So for any circuit C in CC0P of, let's say, depth T, so there exists a polynomial, say, f of x1 to xn over fp. So it's the same, so we're working over primes, and it's the same prime as here. So in particular, those techniques will fail when p is not prime. In general, I forgot to say it before, when p is not prime and we have modular gates, and essentially we know nothing, or almost nothing. So we don't know any hard functions. So if I just give you a constant depth circuit with modulus 6 gates, we don't have to separate it from NP, which is, we don't really believe it's true that you can do all of NP with modulus 6 gates of constant depth, right?
But this then you can do any function, right? So if you have in CC0P for prime P's are functions that you cannot compute at all.
Yes.
And with
Yeah,
modulus 6,
with exponential size, yes, you can do everything. That's true.
so that's a big difference.
Yes. But I think the bigger difference is that all these algebraic techniques don't work there, right?
So, but you can compute any function in CCCP by the same reasoning.
No, so
The reverse of.
no, but okay. So here I just say everything is a polynomial.
No, it's,
So everything which is not a polynomial you cannot compute.
But everything can be computed as a polynomial.
Yeah, but it will have very high degree. So here's the degree will be very small.
Right. But saying it is. Oh, I see.
Yeah.
Even for a fixed depth. You can
Yeah, for fixed depth it will be very small degree.
Right.
Yeah.
But it still doesn't say that for fixed depth you don't have good correlation with
That's true. So yeah, that's true. So, but
Are you specifying the degree?
so I just was going to specify. So if the depth is t, so the degree will be something like p minus 1 to the power t. And this polynomial is exactly computed in f. So, and just p of x is just c of x. So you can always compute such circuit by polynomials where the degree is p minus 1 to the power of the depth. So for every constant depth, it will be a constant degree polynomial. Actually, we have very good correlation bounds for polynomials of constant degree. So again, so this we do have. The problem is that we cannot use them to build pseudorandom generators. Right? Because this is too weak of a family to be used for Smith and Wigderson generators. Okay, so the proof of this claim is really simple. You just do a gate-by-gate simulation by polynomials. So the proof is just, well, remember that what was the modulo p gate? So a modulo p gate of x1 to xn was just 1 if p divided x1 plus xn, which is the same as just taking this sum as a polynomial in fp, raised to the power p minus 1. Right, so this, now if the sum is 0, this is 0 modulo p. If the sum is non-zero, this is 1 modulo p. So that's the opposite. So let's take 1 minus that. Okay, so this is just a specific polynomial of degree p minus 1, and we can replace each modulo p gate with this specific polynomial. And then we just iterate it, and we get this degree. So essentially, the question is about polynomials. Okay. So what we really need to construct is pseudorandom generators for polynomials, but when those polynomials are inputted bits. Okay. So I'm going to talk in a second about what is the usual notion of a pseudorandom generator for polynomials, where you give them field elements, which is a natural thing to give them, elements in FP. Here we want something bizarre. We want to give them bits that look like uniform bits. Now, if you're working in some field F3, uniform bits is not a natural object there. So somehow using those natural algebraic techniques doesn't work as easy. So let me just define this now formally.
Do you know to separate polynomials from circles? You just show this polynomial. Maybe it's much stronger.
But not much, right? So you can always do it with a circuit of depths, p to the power t, right?
You know.
Right, so if you give any polynomial of a constant degree,
Yeah.
so then you just have a polynomial number of monomials. So you just need to sum those monomials. Each monomial is the end of a constant number of bits. Oh, okay. Yeah, the constant depths will increase, but still constant depths. Okay, so I want to give you two definitions. One I'll call bit PRG for polynomials. And the other one will be PRG for polynomials, which is a more usual definition. And then we'll see the difference. So bit PRG for polynomials is what we really need here. So we need a generator mapping a short seed length into n bits such that, well, g of x, let's say if x is in 0, 1 to the r, or just uniform bits, so those are indistinguishable by polynomials, right? Now, what is the usual definition of PRG? So we ask you, again, given r bits, but now generate n field elements. And we require that, again, g of x will be indistinguishable from fp to the n. Okay. So this is, I guess, the notion that people have studied more. And the reason is it's much more natural, right? You have polynomials over fp, so it's natural to feed them inputs in fp. And this is a notion that we need in this talk. And I want to mention that for this model, we do have good pseudorandom generators. So here we have efficient pseudorandom generators. So that's, I guess, Bogdanov and Viola, and myself and Viola. And so here the seed length will be something like constant which depends on d times log n over epsilon. This constant is not the right constant, it's like 2 to the d. We really want it to be d, but for now d is constant, so we don't really care. So here we really have good efficient pseudorandom generators. And now,
That's just the sum of epsilon values.
true. Right, so here you just, so you just take something that full linear polynomials is just epsilon biased. Something that fools all, so over F2, you just need some distribution that fools all linear combination of bits. And over Fp, you have things that fool all linear combination of field elements. So those we know how to construct, and then they show that if you sum d independent copies of them, it's very, very small errors, and this will fool the greedy polynomials. So this constant here is really 2 to the d because you need tiny error in each one of them, epsilon to the 2 to the d in order to fool the greedy polynomials with error epsilon. And somehow what we'll try to do is try to use those and build bit PRGs. And so there is a very naive way to try and do it. It's to say, well, maybe you can just simulate random bits by elements in Fp. So if I give you uniform elements in F3, maybe you can just try and somehow use some low degree polynomial on them and get some uniform bit, right? So, but if I just give you one element, then you can't really do it. So one element will just have 3 values, each equal probability 1/3. So however way you map it into 0, 1, one value will be like have a probability either 0, 1/3, 2/3, or 1. It will never be very close to 1/2. But maybe if I give you many, many elements, you can then this argument doesn't work anymore, right? If I give you an unbounded number of elements, maybe you can use some low degree polynomial and map them into a bit that is roughly half 0, half 1. So in fact, you can show this doesn't work. If you fix the constant degree of a polynomial, then it doesn't matter how many inputs elements you give, you can never be very close to random bit. So this just simple argument doesn't work here. So you really need to study this model more carefully. Okay, and now, so the goal will be how to construct bit PRGs for degree d polynomials. And I'll start with describing the simplest case, which is degree 1 polynomials, which was actually some previous work that was the basis for our work. And it actually will show the main ideas that come into the proof.
So can you please repeat the difference? I'm not sure.
Sure.
Left and right sides.
Okay, good. So it's a very good question. So because it's a subtle difference, but the subtlety is very important. So here, what I ask you to give is field elements that look like uniform field elements. Here, what I ask you to give is bits that look like uniform bits. Now, if the field is F2, it doesn't matter. But if you're over F3, then it's not clear how you connect those two things together.
Okay, and when what you said after is that you cannot just do what?
So a simple way, so what is a simple approach that doesn't work is to just simulate random bits. So what do I mean by that? Assume I had some magic polynomial, let's do it capital P, of many bits, x1 to xn. M can be very large. So this is a polynomial that lives, let's say, in F3, okay? And I know that the probability where x comes from F3 to the m, P of x, so P will always be, so P will be a mapping, from F3 to the m to 0, 1. So we can always make it 0, 1 by squaring it, right? So that's not really a main issue. But what we really want is the probability it's 0 will be roughly half. And the probability it's 1 will be also roughly half, right? If you can approach half very, very well by taking here some constant degree polynomial, where here m can be even polynomial in n, will be good, right? You could just plug this polynomial in, and then fool this polynomial concatenated with our original polynomial. And what I said is that if you require this polynomial to have constant degree, then you cannot really be close to half. So what you can show is that if this has a degree, I don't know, k, then this minus half is always larger than some delta which depends on k, and which doesn't really matter how many variables you put in here.
So there's a specific polynomial which will distinguish between...
No, there's no specific. For any polynomial of degree k that you give me, that maps f3 to the n to 0, 1, if you ask me what's the probability it's 0, it cannot be arbitrarily close to half. There will always be some distance from half. Well, this distance does not vanish when you allow more and more variables. So if you take functions which are not low-degree polynomials, you can make this go to 0. But if you require it to be a low-degree polynomial, this cannot go to 0. There is some fixed bound there.
So the intuition maybe is that if it's a linear polynomial, then it's a subspace, and then the probability can be only 1/3.
Exactly.
It cannot be close to half. And somehow something like this holds for half.
Yes. More or less, yes.
So a linear polynomial cannot have range 0, 1.
Exactly.
Unless it's 0.
So, yeah.
So let's say if it's a square of a linear polynomial.
Yeah. Okay. So as I said, this simple approach doesn't work. So I want to show you. So can you see it here, or does this block? That's fine. So we want to start with just d equal 1. That's a basic case where we want to beat PRG for linear polynomials. So that's actually some previous results. So that's self with Omer Reingold, Luca Trevisan, and Salil Vadan, and also Raghu Meka and David Zuckerman. So we studied this problem for linear functions for a different reason, because they are related to some space-bounded computation. But somehow, what we really want to do, we want to full linear sums, right? So we say, so what we want? So we want this generator, right, that maps r bits into n bits, such that if you look on sum of ai xi, so those are polynomials. So ai's are elements in Fp, xi are our bits, 0, 1. We want that those polynomial cannot distinguish g of 0, 1 to the r from 0, 1 to the n. Okay? So that's our goal for linear polynomials. We want linear polynomials not be able to distinguish outputs of our generator from uniform bits. Okay, let's do it here. Okay, so I said that you don't really have a hope to simulate random uniform bits using polynomials. But what is easy to get is biased bits, right? So if let's say x1 to xn were uniform elements in Fp, and I take yi to be xi to the power p minus 1, yi is a bit, but now it's a biased bit, right? So this is an element in 0, 1, and the probability that yi is 0 is 1 over p, and the probability that it's 1 is 1 minus 1 over p. Okay? So it's easy to get biased bits. So you can ask, okay, maybe generating biased bits is enough. What we really want to fool is uniform bits. But maybe our polynomial cannot distinguish uniform bits from biased bits. So it's enough to fool biased bits, and to fool biased bits is easy, right? So let's look at this case. So assume, let's define this distribution of bits by, define this distribution. This is UP. So UP will just be this distribution over 0, 1 to the n, where each bit is 0 independently with probability 1 over p, and it's 1 independently with probability 1 minus 1 over p. So assume that our polynomial, when we apply it to uniform bits, or when we apply to biased bits, those are indistinguishable. So the output distribution of a polynomial on uniform bits or on biased bits is the same distribution. Then I claim we are done.
What do you mean by biased bits?
So biased bits, I just mean what I mentioned here is that each bit is 0 with probability 1 over p, where p is a field size, and 1 with probability 1 minus 1 over p. So we just choose this. Okay, so the reason is,
What's special about that?
okay, so it's easy to simulate it with operations on field elements. So if I give you a uniform field element and you just raise it to the power p minus 1, you get a bit and it's a biased bit. So those are just distributions that are easy to simulate using field elements. Okay. What I say is that this is the easy case where your polynomial or your linear function cannot distinguish those, because then it's enough to fool that, which is easy, in order to fool that. So how do we do it? So let's just do it formally. So define a new polynomial, f prime. So f prime will be a polynomial in y1 to yn, and it will just be f of f y1 to the power p minus 1, yn to the power p minus 1. Because this will be a polynomial, so if this polynomial was linear, this will have degree p minus 1. Okay? Right, so it will just look like something, so this will just be something like the sum of ai, yi to the power p minus 1. So this special polynomial. And as I said, now if you want to fool, if we fool this f prime over field elements, it will be the same as fooling f over biased bits. Okay, so let's just do it formally. So let G to Fp to the n be a pseudorandom generator. So it outputs field elements for polynomials of degree p minus 1. So we know how to construct those. So we really only need them for this special type of polynomials, but we have this big hammer, so we might as well use it. So it doesn't cost us anything. So we'll use this general pseudorandom generator for degree p minus 1 polynomials just to fool this special type of polynomials. So what do we know? So we know that, let's say, the probability that f prime of g of x, let's say 0, this is very close to the probability that, what do we have? That f prime over uniform field elements is 0, right? This is just by the definition. Here we apply f prime to uniform field elements. Here we apply it into output of the generator. And we see in this generator output field elements that look like uniform field elements. Now let's translate back from f prime to f. So what is this? So how did we define f prime? We just took each element and we raised it to the power p minus 1. Right? So this is just equal to the probability that f on the biased distribution output 0. Right? Because we just simulated the biased distribution by taking field elements and raising it to the power p minus 1. And what do we have here? So here we can just say, well, this is just equal to the probability that f applied to this g of x raised to the power p minus 1 is 0. Here I just mean raising each individual element to the power p minus 1, which is the same as asking either 0 or non-zero. Right? Same thing. So this is now a specific generator that maps the inputs into bits. And we know that those two cannot be distinguished. But if our polynomial has this special property that it's in some ways stupid, it cannot distinguish uniform bits from biased bits, then we're essentially done. Because we know that this is roughly just the probability over f over uniform bits being 0. Right? Okay. So again, what we had, if a polynomial had this special property, then its output distribution over uniform bits or over biased bits is roughly the same distribution. Then, well, we want to fool this distribution over uniform bits, but it's enough to fool this distribution over biased bits. And to fool the distribution over biased bits, we can just cheat, right? We can just define this new polynomial where now we want to fool this polynomial over field elements, and this we know how to do. We just use the tools that we already have. And now, I want to say that for linear polynomials, it's really easy to understand when they cannot distinguish uniform bits from biased bits. So tell me, so I give you a linear polynomial. When can this polynomial distinguish between uniform bits and biased bits?
Yeah, if it's one variable, for example.
If it's one variable, for example, it will be able to distinguish.
If it's a sum of many, then it will be more difficult.
Exactly. So the only parameter that matters is how many non-zero coefficients it have. Right? So if f of x is this sum of ai xi, the only parameter is the number. So if the number of non-zero coefficients is large enough is something like p cubed log 1 over epsilon, then essentially this polynomial cannot distinguish uniform bits from biased bits, because they both mix, right?
It has to do with the invariance principle?
No, this is really,
Just computation.
it's just computation, but another way to say it is that what we really do is you're mixing, right? You have a distribution here, and now you sum more bits and more bits and more bits, and you're just, think of p as 3, okay? So you have, first bit is uniform, right? So it's your 0, 1, half, half. You sum another bit. So now your distribution becomes closer and closer to the uniform distribution, right? Actually, after even p squared log 1 over epsilon will be very close, epsilon close to the uniform distribution. I can do exactly the same argument, but now each bit is biased. So now you need to sum more of them, because each one is really tends to be just one specific value. But if you sum p cubed log 1 over epsilon of them, then this also will be very close to uniform. And those two distributions will be very close to uniform, so
Type?
what?
No.
It should be p squared?
So it's p squared if it's a uniform, but if it's a biased distribution, you need p cubed. Because we need to be true also for the biased distribution, which is 0 probability 1 over p.
Yes.
So the number of iterations that you need is something like p cubed. You're asking whether this
P squared, yeah.
is it p squared also be enough?
So you want to show that it's uniform either way.
Yeah.
Uniform mod p. So to show that, look at the collision probability for a sample from f of x. So that's picking f of x1, f of x2, looking at whether the difference is 0. Okay. So then you can do that term by term. Okay. So so you're saying, okay, well, let's look at so you look at so let's say one's x and one's y. So you're looking at some ai xi minus yi and saying whether that's equal to 0.
Right.
And if the xi's and yi's are biased with, so you're saying like, sort of look at the last batch of 1 over p, and you expect about 1 of the xi's or 1 of the yi's. Sorry, last batch of p, since the xi's and yi's are biased, you expect about 1 element
Yeah.
to appear.
Okay, I mean, here is a good way to see the. So you look this.
To see what?
sum-
P cube? Or what
To
we
see
say?
p cube log of 1 over x.
The p cube is the right
Yeah,
thing?
no?
Yeah. So basically, this is a random sum of elements, and it's we know that it's a normal distribution. So you just want that, and we know what is the standard deviation of that. So you have to multiply by 1 over p because each variable is bias 1. So so the variance is p squared log of 1 over epsilon, and the square root of that, which is the standard deviation, is p square root of log of 1 over epsilon. So that, and you want that, since we know that it's pretty much uniformly distributed on one standard deviation, and square root log of 1 over epsilon is what in Chernoff gives you this epsilon deviation, then this gives you that it's close enough to uniform. This is
So So I don't know, the easiest way I know to analyze is just to try and look on the characters of it. So assume you want to ask what is that omega. If you just look at these averages, sum of ai xi, right? You want to show all of those are small enough, smaller than, let's say, epsilon over p or something like that. Then this is just the product of those averages. And then the question is how small are each of those? And I need to remember. So I think you get something like 1 minus 1 over p squared, roughly, right? Time to, let's say, xi. And then if those are uniform bits, then you need p squared log 1 over epsilon. And if those are biased, then you need p cubed, right? Again, because just one in p will really be different.
What is WP?
What is, oh, sorry, WP is just e to the 2 pi I over p. It's the pth root of unity. But again, it doesn't really matter if it is p cubed or p squared. P is just some constant, it's 3. So that's not a big issue. Okay, what I wanted to say is that, well, if the number is large enough, then essentially f on the p-biased bit is very close to f on the uniform distribution, and we are done, essentially, right? So now, somehow, the bad case is where this number of non-zero coefficients is very small, right? But this is also easy to handle, because we can just use some k-wise or almost k-wise distribution and fool that. So somehow the bad case is there are few non-zero coefficients, and here we just use, let's say, k-wise to fool, where k is some bound, is p cubed log 1 over epsilon. So actually, if you really want to get the optimal bounds, you need almost k-wise, and not k-wise.
So what does it mean that here, finally, you have to use one distribution?
Okay, essentially. So okay, so how? So we know we have one distribution to one set of polynomials, then another that put another. Actually, if you XOR them together, it's easy to see that if you XOR them together, you fool all polynomials. So I won't show it, but it's just a routine check. Because just XOR in one constant thing leaves just a shift as a polynomial. Each variable just either leaves the same or replaced with y minus x. So it's another polynomial. Okay, so this finishes the argument for linear polynomials. So one thing here is quite general, right? So this argument that says if a polynomial on uniform bits or a polynomial on biased bits have the same distribution, then even for higher degrees polynomials, the same argument will work, right? Because we didn't use anything special for linear polynomials. All we said was, well, we really want to fool that. We don't know how to do it. So we'll cheat, we'll fool that. The distribution over biased bits, and this is easy to do because you can just simulate it over, yeah.
I didn't get your XOR argument. So this is over GF3, right?
Okay.
But you will do XOR over GF2. So you will have two distributions. One of them is the usual epsilon bias over GF2, and the other is this distribution that you got here, and you take the sum over GF2.
Yeah. So assume you have one.
So that's a distribution on bits again.
On bits again, yeah. And the thing is, you can always, if you fix one of them, it's fine, because you take a polynomial over n bits, and you XOR some string to those bits, you again get a polynomial of the same degree, right? Because each variable,
So that's what,
yeah.
So
It should be the same or one.
not over GF.
Yeah, XOR, exactly. You have two distributions of bits, and you just XOR them.
That is XOR. It could be
Any combination.
permutation.
Yes.
Oh, it's just a permutation.
Yeah.
Well, but you want to keep the degree of the polynomial, right?
Okay. Yeah.
So XOR is easiest. Maybe some other, there are more complicated ways to combine them together, but XOR is the easiest, I guess. You just want some combination that keeps the degree the same, if you fix one of them.
Okay. Because it's 0, 1, it's either XL or minus XL.
Exactly. But again, as Russell said, any combination will do, essentially. Okay. So somehow this argument, the first argument, really works for any constant degree. Well, here what we'll really use, instead of this generator for degree p minus 1, we'll use the generator for degree p minus 1 times d. Right, or yeah. P minus 1 times d, right? Because if f was a degree d polynomial, then having this replacement, f prime will be a polynomial of degree p minus 1 times d. So this argument still works. So somehow the bad case now becomes harder to analyze, because now you have some higher degree polynomial. I tell you this polynomial, for some reason, can distinguish uniform bits from biased bits. And now the question becomes why? How can a polynomial, let's say of degree 10, distinguish uniform bits from biased bits? And somehow, so what we'll try to do is understand the structure of such polynomials. So here the structure was very simple. There were just functions of a few, there were just linear combination with a few non-zero coefficients. The answer for higher degree is more complicated. But
still, yeah, so still it seems that if you have like many terms that depend on different sets of variables, then it will not distinguish, right?
yes.
With sum of many monomials.
Yes, but it's not a generic case. So let me give a few examples. Exactly. You can have common variables. You can have products of things. So. So even that is not strong enough. So let me give a few examples. Right, so now the question that we need to understand is, so we have f. So f is some degree d polynomial, and we know that, let's say for example, the probability that f over uniform bits is 0 minus the probability that f over biased bits is 0. So this is not, those are not closed. This is now larger than epsilon. So f, for some reason, can distinguish uniform bits from biased bits. And now the question is, what is the structure of f? And then how can we use this structure to construct pseudorandom generators? That will be the next question. Okay, so give you a few examples. Well, one example is trivial, so just take any, let's say, x1. Right, so if you have just single bits and it distinguishes, or in fact, write any function on a small number of bits. Or you can find functions on smaller bits. But there are more complicated examples. So choose some random polynomials and take something like f1 of x times f2 of x, right? So let's say, sorry, f1 of x times, let's say, x1. Okay, so this is another polynomial. f1 is some random polynomial. Okay, so its distribution is very close to a uniform field element. But x1 is a bit, so it's 0. The probability x1 is 0 is different whether it's uniform bits or biased bits, right? So those polynomials can distinguish, and we can also add here a few of those, right? If you have a few of those, they can also distinguish. So essentially what we'll try and show is that any polynomial that can distinguish uniform bits from biased bits has to look like that.
It's a sum of a few terms, and each term is like really...
So we want to really be able to show it. So if we really want to show exact results, the bounds that we'll get are much, much worse. So we'll only show approximate results, and even those will be of weaker nature, but they'll be sufficient to prove the pseudorandom generator. So I think that as you try to prove more and more concrete results, the bounds that you get become much, much weaker, then you will not get such good bounds.
But it is more or less a structure theorem for all the polynomials that can distinguish between bias distribution and uniform distribution.
Yeah, so we'll show that any one of those can be approximated by some structured polynomial of some somewhat more complicated structures than that.
But here it doesn't matter what are F1, F2.
Right, so you don't need to be tailored, right? So you don't want F1, I don't know, to be minus x2 and F2 to be x1.
Okay.
So you don't want to have some
Okay.
trivialities. So, but choose a random polynomials.
Okay.
Okay. Good. So that will be the question that we will try to study.
You can decide if you want to...
Right, that's what we're going to ask. So I guess if you want to have a break, now is a good time for like a 5 minutes break, if people are interested. Seems like it. Okay, so let's have 5 minutes break. So we said, well, if you have polynomials and they cannot distinguish uniform bits from biased bits, then those we have this simple trick to fool them. And now the question is how to handle these bad cases. Those polynomials, for some reason, can distinguish biased bits from uniform bits. And the question that we ask is, okay, if you have some degree polynomials that can distinguish them, let's say the probability it's 0 under uniform bits or under biased bits is somewhat different, then what is the structure of this polynomial and how can we use it in order to fool it? And we gave you 2 examples. And now I want to give a more general definition and then state a theorem that tells us something about the structure of these polynomials. So the definition will be that of what we call bit rank. So we say that f has bit rank k if essentially it can be, so f is a polynomial of degree d. And then the question will be, how many polynomials of lower degree do we need in order to compute f over bits? So we only care about f over bits, so we don't really care f over any input which is not bits. But over bits, how many polynomials do we need in order to compute f exactly? So again, f is a polynomial of degree d, or any function. So it has, let's say, d minus 1 bit rank k. If there exists k d minus 1 degree polynomials, let's call them g1 up to gk. So those are polynomial in fp to the fp x1 to xn. So they're polynomial over a field, but we'll only evaluate them over bits. So we never evaluate them over non-bit inputs. And we require that for every x in 0, 1 to the n, the value of our function f of our polynomial is determined by the values of these polynomials. So f of x is some function gamma of g1 of x up to gk of x, where gamma is some function from fp to the n to fp. Sorry, fp to the k. So think of k as a small constant, okay? So 10. So it has some function or some polynomial has d minus 1 bit rank 10. If you can give me 10 polynomials of degree, total degree, at most d minus 1, such that knowing the evaluations of those polynomials over our input, which is bits, only bits, we know the evaluation of f. So let me give an example, because what is the difference between bit rank and the more...
So for this definition, f is a polynomial that does not get Boolean values. It gets...
yeah, but it might get, but we'll only evaluate it over Boolean. So f is some function. So it may be a polynomial, be some other function. We don't really care. The only thing is that we'll only ever evaluate over bits, so it doesn't really matter if it's defined over other inputs or not.
No, what I'm saying is that the values that it gets...
oh, the output values.
The output
Yes, in FP.
is in
FP, yeah. So let me give an example. So it's for quadratics. So take f of x to be the sum over I different from j, xi, xj. Okay, so this is a quadratic polynomial, and let's understand its bit rank and compare it to the usual definition of rank of quadratic polynomials. So what is its bit rank? So if you just allow bit inputs, then, well, f of x, we could just write as the sum of xi squared minus the sum of xi squared. Right, that's always true. But because we are over bits, then xi squared is the same as xi, right? So this is just the sum of xi squared minus the sum of xi. So in fact, the 1 bit rank of f is 1, right? If I give you this linear function, you can evaluate f over any Boolean input. But on the other hand, the rank of f is large. It's something like n or n minus 1, depending on whether p divides n or something like that. So Rank is just the rank of a quadratic, which is the same as how many linear functions do I need to know in order to compute this quadratic over the entire field, fp to the n. Right? So even if p is 3, to compute it over f3 to the n, I need roughly the maximal number of linear functions I need, either n or n minus 1. But if I just want to compute it over bits, I just need one linear function. So in general, there can be a very big distinction between bit rank and rank.
So this gamma, capital gamma is, what's the condition?
Some function, I don't care.
Any function.
So you should think about it as, if I know the value of g1 of x up to gk of x, I can determine the value of f of x.
Okay, that's all.
So gamma is some way to determine them, I don't care. Okay. Good. So now this will be our theorem on the structure of polynomials which can distinguish uniform bits from biased bits. So we say something like that. So let f of x be a degree d polynomial such that, let's say, the probability that f over uniform bits is 0 minus the probability that f over biased bits is 0. So this is not too close. This is at least epsilon. Okay, so they can distinguish uniform bits from biased bits. Then for every error parameter delta, we can essentially approximate this function very well by a function that has small d minus 1 bit rank. So for every delta, there exists some function g from 0, 1 to the n to fp such that, well, on the one hand it approximates f, so the probability over bits that f of x is equal to g of x is 1 minus delta, so it's correct almost everywhere. And it's the d minus 1 bit rank of g is small. Small is some function of the parameters. But this doesn't depend on the number of variables. So small is some function of the degree, the error, how much they can distinguish, and which is the delta you want to take. But it doesn't. The crucial part, it doesn't depend on the number of variables.
So d, epsilon, p, and delta.
Exactly. Yeah, so it's something like, so it's k, which is some function of p, d, epsilon, delta. Okay. And sorry, and delta.
And this is this terrible function?
And it is exponent. So so okay. On the one hand, you can think it's terrible because it's a tower of exponentials. On the other hand, it's quite good because many times the theorems we get in this field, we have towers of lengths of towers of lengths of towers and so on. So just to have a single tower is actually quite a good constant. Yeah.
But then you have to apply it recursively.
No, so you don't. So the reason we get only single tower, not towers of towers, is because we have your approximation. If you'd require to have exact computation, we'd really get something like towers of towers and towers and so on. Yeah. Yeah.
So then, it's not clear why
Yeah.
you need, why.
You're asking, is there a lower bound? Do we really need something that big?
No.
Yeah.
Saying, okay, so each of the g's, okay, g has d minus 1 rank, small d, g minus 1, d minus 1 rank.
Yeah.
But then you're writing g as some function of g1 up through gk.
Yeah.
Okay, and now you need to fool g1 through gk.
Yeah.
So don't you have to apply it recursively?
So no. So
d minus 1 to analyze each of
yes.
the
So this theorem doesn't need recursion. To build the pseudorandom generator, you use it recursively, but the error doesn't accumulate that much. So it's not really a major issue.
So is errors only k times what it was, or no? Oh, I see. Yeah.
So I want to say, okay, so one thing I want to say is that why can you get from this theorem the result by reduction. And there is one non-trivial part about it. So
Because you have to go from one polynomial to multiple.
no, that's actually that's the easy part.
What's on the delta? How
Okay.
depends on the delta?
So again, so what?
So how does this tower depend on delta? Is it if it's very sensitive to delta, that might be what, as Russell said.
I think I don't remember. I think the length of the tower is the same, something like p to the d or whatever. But on the top you get some polynomial in epsilon and delta or something like that, or in epsilon log 1 over delta. So it's not really dependent on delta. So I won't do it in full details, but there are two steps, right? So one step, which is the easy step, is that, well, we can also fool G. And the reason is, right, so if you take PRG, or let's say bit PRG, for degree d minus 1, they also fool G. So we know they fool a polynomial over degree d minus 1 divided over bits. Now G is some function, let's say gamma of, let's call it G1 up to Gk. So each one of those we can fool. Actually, you can fool all the linear combinations of them, right? Each linear combination is again a low degree polynomial divided over bits. So if you can fool all the linear combinations, then essentially you can just fool G, because we fool all the Fourier coefficients of it. So I don't want to do it in details, but that's the easy part. The somewhat harder part is that this condition is not.
Fooling.
Yeah.
Okay.
Sorry. What?
But you would need degree d minus 1 that epsilon over k fools.
Yeah. So it's a better error for d minus 1 and not to fool. Actually, it's actually much better. Because you need, there is another step here that I didn't say. So one thing that you need epsilon over k or epsilon over 2 to the k. That's one thing that you might need. The other thing that you need is that the approximation here is not good enough, right? What? Because you have 2 to the k Fourier coefficients here. The Fourier coefficient of gamma. You have 2 to the k of those, and you want to fool all of those. And then just the union bound, let's say. Okay. The other case is that, well, this approximation is not strong enough, because it says that, well, over uniform points, f and g are really close together. But this generator is a tiny sample set, right? So maybe this tiny sample set fools always where f and g differ, right? It doesn't mean it's uniformly spread around.
You mean because of the bias?
No. Then I have a function. So I have a PRG for this function, g. This function approximates it very well. It doesn't mean it's a PRG for g, it's also a PRG for f. Right? Because this PRG is this tiny set that looks like the whole set. But maybe this tiny set is always where f and g are different. Right? So you can say anything there. Because it's tiny, and this delta is just some small constant. So do you understand the problem?
No. Okay.
Okay.
So this difference is defined over z1 to the n anyway.
Yeah. So it's a distribution. So
F and G are equal almost always, but maybe they differ over every element of the PRG. The PRG gives
PRG is some right. So okay.
So,
So do everybody understand the problem?
yeah.
Okay. And it turns out, so what you need to do is you need to get this stronger notion of a bit PRG. So what you can get is a distribution over, let's say, h, some function h, from 0, 1 to the n to fp, such that we have two things. Well, again, each h has small d minus 1 bit rank, but now we have a uniform notion of approximation. So for every x, the probability that f of x is equal h of x is at least 1 minus delta. Okay? So that's now a uniform approximation. Okay. So what we had here was just some function that approximates your function everywhere, almost all the points, right? So it's this non-uniform approximation. You're correct almost everywhere. At some points, you're really bad. And here I'm saying what you can get, I'll say how in a second, is this stronger notion of approximation. So I get a distribution over functions. And if you choose it, so for every point that you want, most functions are correct. And now this problem doesn't occur. And the way to get this stronger notion is just to use the fact that our function is a polynomial and use self-correction for polynomials. So we can use self-correction for polynomials to define this distribution. So I don't want to do it here, but that's the high-level idea of how you do it. Okay. So now, what I want to talk about next is how do we prove this theorem, and this will be related to the Fourier spectrum of polynomials. So, but before that, are there any questions on how do you get from this theorem our main result, like for the PRGs? So just apply the things.
You apply it by induction on the degree and.
Yeah, so you have two constructions. One is like if your polynomial is nice and cannot distinguish uniform bit from biased bit, we have this simple construction. If it can distinguish, then we have this recursive construction that says, okay, it's enough to fool lower degree polynomials with much better error in order to fool this polynomial. And then as before, we just XOR those together, and this fools all polynomials. Okay. Another question is how do we prove this theorem?
So you will get a single h that is equal to f with respect to the uniform and the pseudorandom distribution. I mean, so.
Oh, you mean from that? That's one way to do it. Yeah, that's one way to do it. Yeah. Okay. Okay. So how do we prove this theorem? So in general, what can we say about polynomials that have some non-pseudo-randomness properties? So this is an example of a polynomial that exhibits something which is non-random, not random, right? It can distinguish uniform bits from biased bits. It has something. So one thing you can say is that, well, one of those distributions, right? So what we know? So we know that f over uniform bits and f over biased bits are somewhat apart. And I want to say that this means that, well, one of them has to be not very close to the uniform distribution over the field, right? If they were both very close to the uniform distribution, then they'll be close together. So one of them is not too close to the uniform distribution over Fp. And for this talk, let's assume it's this one. Actually, this is an easier one. Because this one, if we have this one that's not too close, we'll actually show that we just transform it into something that having that the bias distribution where some of the bits you shift by something being not too close. The thing is, those distributions are easy to work with because we can simulate them by some higher degree polynomials like we did before. Okay, I don't know if this was clear or not, but for this talk, let's assume that this distribution is not too close to uniform. And the other case is very similar. So what do we know? So as before, right? So we can define this new polynomial, right? Because the intuition is, okay, working over bits is hard. We want to work over field elements because there we know some things, right? So we'll define this new polynomial. So f prime of y1 to yn will just be f of y1 to the power p minus 1, yn to the power p minus 1. And so what do we know? So we know that f prime over uniform field elements is, so let's say, epsilon far from the uniform over Fp. Okay? Good. Now, we know properties of polynomials which are do not have uniform distribution. There are easy ways to show that they have nice structure. So here is a lemma which was first proved by Bogdanov and Viola. And it says the following thing. So let's say f prime is not close to uniform, then we can approximate f prime by a few derivatives. I'll define derivatives in a second, but the idea is somehow to use induction, right? We have some polynomial of degree d, derivative with degree d minus 1, somehow we'll approximate by them, it will give us some structure. So what are derivatives? There will be this discrete derivative, so the derivative of f prime in direction y will just be f prime of x plus y minus f prime of x. Right? So think of the x's as variables.
F of x plus y.
Sorry, f prime of x plus y minus f prime of x. Okay. So think of the x's as your variables, the y's as some constants, right? Then if you open brackets here, then all the terms depend just on x cancel on both sides. So you just get these mixed monomials in x's and y's, and those will have degree smaller in x. Okay. So this is a derivative. So what they show, so they show that under this condition, well, you can always write f prime of roughly, so it will be approximation, a sum function of small number of derivatives. Yk of x. Okay. In fact, this function can just be the majority function. So you can just take a small number of derivatives, actually random derivatives, and just take the majority, and this will approximate your function almost everywhere. And the indication why this works is the following. So we have a function, right? So this is a function f. And assume it's 0. It tends to be 0 more often than it should be. Then if you take a derivative here, right, this is f prime y, then we can guess this is 0, right? And it will be correct more often than random. So you can say, well, we can really approximate this function by this derivative. Intuitively, this should work, right? Because this point tends to be 0 more often than otherwise. And you can make this work, right? So that's the intuition behind it. And if you just take in a random derivative, if you take a single point here and take a random derivative, it's the same as choosing the other point as a uniform point in the space, so we know it will tend to be 0 more often. So the derivative will tend to be equal to the function more often than random. And then just taking the majority of a small number.
The assumption is if f is not close to a uniform.
I mean, if the distribution
What kind of feature? Is it
f
over 0, 1 to the?
the f prime is some function. So now we'll have this fp to the n to fp, right?
Or are you making a generic statement like this is true for?
It is true for any
Okay.
polynomial, or in fact any function. Any function, but for polynomial, derivatives simplify the expression. For general functions, derivatives might be as complicated. But this is true for any function.
So take any function that's not close to uniform over fp.
Over fp, not close to uniform over fp. So the output distribution is not too close to uniform over fp. Let's say 0 occurs more often than it should. Then you can always just say, take a small number of random derivatives, take their majority, you'll be correct with high probability, and then if you choose the number here large enough, you'll get here to be correct almost always.
Sorry, here the number, does it depend on the degree of f prime?
No. This is an argument that's true for any function. So the proof is 3 lines. I don't want to do it 3 lines.
The intuition you said is a proof.
Yeah, it is the proof.